Welcome everyone. Okay, so Chiara showed you what we can do and what we can learn actually with gravitational waves from the early universe. Here I will focus more on the late time universe. So by late time I mean basically up to redshift, say 8, 10 probably. We will see. But in general, the idea is to use gravitational waves in a different way as compared to what Chiara has been showing. This is because we will look at sources which we can identify and specifically locate. Okay? To do this, I will need to introduce some concepts, and in particular, I would like to. So my goal here is to give you a few concepts. A few basic concepts, and try to explain them to you. And in particular, I will try to define what is a standard siren. Also because I've been told that actually maybe here half of the audience is not familiar with general relativity. I don't know if this is true. Okay. And I was just wondering, so how many of you are familiar with Bayesian inference? Okay, cool. Hierarchical Bayesian inference? Okay. Yeah, because I will need that later on to explain how we actually do this analysis. But okay, so without further ado, I will try also not to go beyond the time that it's allocated for me. So maybe I will take 5 minutes more. Okay. Also because I will continue on Friday. Okay. Also, I'm actually a researcher. I work in the LIGO-Virgo Carrier collaboration. I've been recently working on the latest paper that the LIGO-Virgo Carrier collaboration released on cosmology, with gravitational waves as standard sirens. I will tell you a little bit about it. This will help me probably on Friday to move to specific sources that we can use also in LISA. Okay. So again, here I don't know exactly what the background is, so let me just put a slide on the basics, and in particular on the FLRW cosmology. So what is the idea here is that on a gigaparsec scale, the universe is homogeneous and isotropic. Okay? And one solution of Einstein equations that we use actually to describe the space-time of the universe is given by this expression here. Okay? This is called Friedmann-Lemaitre-Robertson-Walker metric. And as a metric, it gives us basically the description of the geometry of space-time. There are some ingredients which are useful here for us. And in particular, I want to point out that we have a function which is called A of t, which is called scale factor. Basically, this tells us how the spatial part, if you want, of the metric changes as a function of time. Notice also that this function is basically a factor which multiplies the three other comoving coordinates, the spatial comoving coordinates. Then we have, a radial component, and then we have theta and phi, which are the usual angle that we use. K here is a parameter which describes the geometry. In general, we can have three kinds of geometries, like an open universe, a flat universe, and a closed universe. Here, what I mean by the geometry, imagine your space-time in 4 dimensions. Take a slice in time. Now you have a 3-dimensional space. This geometry here refers to this 3-dimensional slice. Okay? Okay, this is like the metric that we use to describe basically how objects are, disposed in the universe, displaced in the universe. Now I want you to consider 2 points. Imagine in this moving coordinates frame. One, I put it at the origin, and the other just at a radial distance r. So they share the same angles, right? Theta and phi. And we can define a quantity which is called proper spatial distance, which is basically the physical, if you want, the physical distance, spatial distance between these 2 points. And to compute that, you basically take the spatial components of your metric tensor, right? Gij, which is just given by these terms here. And you can just compute, you just take this, right? You take the components, these three components, and then you integrate to get a finite quantity. And you get this equation here. Now, in the case of a flat universe, which is basically what I will use for the rest of this lecture, k goes to 0, right? We can just integrate this, and we get this expression for the proper distance. OK, what do we do with this? Well, OK, this is a quantity which actually will come out in the polarizations of the gravitational waves. So I just wanted to define it here, because later on you will see this quantity. Now, in case of an expanding universe, another thing I want to say is that an observer which is located at R0, for example, and that receives, for example, an electromagnetic or a gravitational wave signal, which is at R, will experience basically time dilation. The consequence of this is that an interval time that I measure here in my frame will be basically dilated by a factor, dilated or in principle compressed, but we know that actually cosmological action, because of the expansion, will be a dilation. It will be dilated by this factor 1 plus z. Okay? Here O and S refer to the, I'm referring to observer and source frame. Now, if you take this expression, you can convert it easily in terms of frequency. You can express it in terms of frequencies, and you get, if you want, reduction of the frequency, in the sense that the frequency that we observe will also be kind of smaller because of this 1 plus z factor. Okay, very quick exercise. I will not do it here, but I just suggest you, starting from the condition the s squared equal to 0, right, which you can take from here, you can derive basically this expression. Okay? Okay, now I will, this was like my introductory cosmology slide. Now we'll move to gravitational waves and the polarizations. So what I'm going to do here is to show you explicitly why gravitational waves are standard sirens. I think that maybe last week in one of the courses, it has been mentioned already that actually the polarizations have a factor, you know, the luminosity distance, and that you need to basically account for that if you consider sources at cosmological distances. But here I just want to, you know, to go step by step and show you how this actually comes out. Okay, I'm considering here a binary system, point sources, very easy, Newtonian, basically Newtonian system. The quadrupole formula, you have already seen it. I'm not going to show you here. But basically, you can use that formula to derive an expression for the power emitted by the system. This gives you, if you want, you can use this expression in terms of a conservation of energy equation, and then you can derive some expressions for the polarizations. The polarizations of gravitational waves, we have two polarizations in GR, H plus and H cross. So there are different terms here, right? Basically, what we have to do here to account for the expansion of the universe in the local wave zone, which is like, imagine a region which is not too far from the source, but yet in such a way that still, like the polarizations already have a decay that goes as 1 over r, but also, you know, sufficiently far away that effectively the factor A, the scale factor, is important. So we have to put it there. So these are like the expressions that I think you may have already seen. In particular, so here I'm expressing the polarizations in terms of a time which is measured by the clock of the source, so in source frame. There is a quantity here which is called MC, which is the chirp mass. This is a parameter, very important parameter, because it's basically the first, you know, the first parameter that we can actually constrain already at very low order. And it's given by a combination of the two masses that we have in the binary system. Here I'm expressing the frequency of the gravitational wave as a function of the retarded time, which is defined simply as the time minus r over c. This is to account for the fact that as the gravitational waves propagates, it does so at a finite speed. Okay, so we will have some kind of delay. And then you have other terms here. For example, we have these functions, which are basically geometric functions called iota. Iota is an angle, which is very important. It's the angle between the normal to the orbit of the binary system and the line of sight. So for example, usually when you read a paper on gravitational waves, you may come up with, we consider a phase-on system, we consider an edge-on system. This simply means that, for example, the binary system, when it is phase-on, it's like this. So the binary is like here, okay? When it is edge-on, it's like this, and when it is like phase-off, it looks like this. And the angle iota simply describes these three cases. Of course, you can have intermediate cases, okay? Right, so, and then you have the phase, right? These are like the phase that you can express, again, as a function of the frequency of the gravitational waves, which you can integrate to get also an expression. And the important point here is that the gravitational wave frequency evolves in time, right? Because as the binary system emits gravitational waves, it shrinks, and therefore the frequency of the gravitational wave emitted increases. And this is the expression that you can derive also from the quadrupole formula, basically, where you see already the important concepts, right? There is tau s to the minus 3/8. Tau is the time to coalescence. So as we approach the coalescence, basically, as the two bodies approach each other, the frequency increases. And then you have the other important parameter, which is the Chirp mass here, which also is a denominator, meaning that, in general, as the mass increases, as the mass of the system increases, the frequency will go down. And this is what we also observe in NVK. In Laghi-Virgo-Kac detectors, for example, when we have like a massive system, by massive I mean, for example, say 100 solar mass and 60 solar mass, it will probably kind of merge maybe at around, say, 60, 70 hertz, while smaller masses will tend to merge at higher frequencies. For example, 150914, which was the first detection, it's a 30 plus 30, say, solar masses, and the merger frequency was around to 150 hertz. Neutron stars, even small mass, and you will have basically a merger that you will not see because it will happen like at very high frequencies. Okay, this is just something that I think you have already seen. Now, imagine that this is my system. That's us. And the gravitational wave basically propagates, right, in the FLRW universe. Now, if the source is at cosmological distance, one has to account for the fact that the scale factor has evolved during the time of propagation of the signal, right? One can show, basically, that the main consequence, compared to the equations that I have showed you in my previous slide, is just to replace the scale factor with the value of the scale factor today. In other words, previously we had like this expression where we had the scale factor evaluated at the time of emission of the signal, of the GWs, and one just has to replace this, okay? All of the rest basically stays the same. Okay, so far so good. This is indeed the proper distance that I defined at the beginning. But actually, we are not really interested in these expressions for the polarization. Yes?
The scale factor in the previous slide
yes.
was related to the expansion of the...
This one?
No. Go.
Ah, the scale factor, sorry.
In the previous... Go on. Okay. Here.
Mm-hmm.
I thought this was mere quadrupolar without cosmology involved. But there is an A of TE.
Yes.
Which
because here I'm considering, again, this polarization is in the local wave zone where I'm assuming that I'm already sufficiently distant from the source that the scale factor starts becoming important. And so you have to include it if you want. I mean, you could in principle, okay, the basic expression is without this.
Okay.
This is when you are starting, going kind of away and far away. And basically, again, instead of having A of TE, now we have A of TO. But again, these quantities here are expressed, the frequency in particular, is expressed as a function of the time in source frame, which is not really what we actually measure. Yes?
Don't you use the redshifted masses here?
Sorry?
The masses are not redshifted here, or?
No, not yet.
Okay.
They will become
Okay.
shifted. I'm going to show it to you in one slide. The next slide. So yes, other questions? Okay. What I want to do now is to express these equations in terms of the time and the frequency that I observe. Okay? And what happens here? Basically, I'm replacing the frequency of the gravitational wave, the expression, as a function of the time measured in the source frame with the same expression measured in the observer frame. And to do that, basically, you gain one factor here, 1 plus z to the 2/3, because you have the frequency at the observer in the power of 2/3. I showed you previously, right, that we have to, basically this gives you a factor, an additional factor that accounts for the expansion. The other place where you have to replace the expression for the frequency is also in the phase. One can show that basically it doesn't change as compared to my previous expression. The reason being that we have a dt factor and an f, and the factors of 1 plus z simplify. So the phase stays the same, okay? The gravitational phasing does not change because of this. But what changes is the frequency, because now this is the observed frequency. And this gives us a factor of 1 plus z to the power of 2/3. Now, I divide and multiply by 1 plus z, right? I'm getting 1 plus z to the 5/3 divided by 1 plus z. I can do it. And then this gives me the expression for the luminosity distance. Why? Because now this is what is usually defined as the luminosity distance. Here basically you have again the proper distance multiplied by a factor of 1 plus z. And here I defined another quantity, which is mc, curly mc, which is given by the previous mc that I had multiplied by 1 plus z. Okay? And this is what we call redshifted Chern mass. Why? Because now we have the Chern mass multiplied by 1 plus z. And this gives me also the luminosity distance for free, basically. Okay? So the reason why we actually have the L in the expression of the polarizations is because basically we are expressing the quantities that we have in the polarizations from source frame to the observer frame. This definition, I don't know if I have to show it, but basically it comes out of the definition that you can obtain by defining the flux, right? For example, for electromagnetic observations, you can define the flux as given by the luminosity of the object, which is emitting electromagnetic signals, divided by 4 pi r. In my case, r is given by this, the proper distance. Then I account for the fact that L, so I mean, the flux is given by L divided by 4 pi Rp. The luminosity here is, I can express it basically as dE over dt divided by 4 pi Rp. And now you have to account for the fact that these quantities are expressed in terms of the observer frame, right? And so basically what you do, you want to rewrite these two quantities in terms of source frame quantities. And this gives you basically a factor of 1 over 1 plus z, because if you think about the energy, I mean, just taking a quantum mechanics argument, you can write it as h bar omega, right? It's a frequency, so the frequency gives you a factor of 1 over 1 plus z. And you have also another t, a dt, a denominator, which gives you another factor of 1 plus z. And so basically you end up having the, yes, in the source frame divided by dt in the source frame times 4 pi 1 plus z squared Rp squared. And this is what we define as the L in general. And this is what we get there. Okay.
There's a square missing, I think.
Sorry?
Square.
Sorry?
Yeah, the DL has to be squared, right? Because you're doing.
Oh, yeah, sure. Yes. Thanks. Okay. Yes.
Thank you. Okay, so if I understood, you got a redshift factor on the frequency, and then you just shuffled 1 plus z's around to make a luminosity distance appear, and this is why we talk about redshifted masses instead of redshifted frequencies.
Yes.
Right? It's just convenience for interpretation, right?
Yes.
Okay.
Exactly. All right.
Where does the 1 plus z to the 2/3 come from? I missed that in the first line.
This one,
Yeah.
from the expression of the frequency.
Okay. Cool. Thank you.
Because you have like, here I am expressing the frequency in source frame. And now I'm replacing this by the proper expression in the observer frame. And as I showed you also here, this gives me factor 1. And I have the power 2/3, so...
Okay. Thank you.
Okay. Okay, another small exercise. You can check that the expression that you obtain here, you can, check explicitly that basically this is equal to the same expression that you have for the frequency in source frame, except that you have to replace now the tau s with the tau 0, okay, and which is defined like that, and also now you have the redshifted chirp mass here. But basically, it's the same expression that I showed you in my previous slides. Okay, now, what is the point now of standard sirens? So the point is that by looking at the phase evolution, so we have, for a gravitational wave, in principle, we have the polarization expressed as a function of, we have an amplitude and we have a phase. Now, by analyzing how quickly the phase evolves, this gives us information about the evolution of the frequency as a function of time. And we can look at, for example, this equation here, which is again something that you can derive from the expression that I gave you before for FGWO, which is again something which comes just directly from the quadrupole formula. You take the derivative of the expression that I showed before. And you see that basically this equation connects the evolution in frequency, the evolution in time of the frequency with the frequency itself. And there is the chirp mass here, right? The redshifted chirp mass. So the point is that if I'm able to measure the phase of the signal, I can get a constraint on the chirp mass. Because basically, I'm observing this. This is something else that I can also, track down. And I can constrain the chirp mass. Now, the next point is, these are like the expressions that I have. If I take the ratio of H plus over H cross, so assuming again that these are kind of known constants, if you want, to the phase, the amplitudes basically simplify, right? Because we have these factors simplify, and what I'm left with is basically the ratio of these functions of iota. No? Iota was the inclination angle. And then I can solve this equation and basically get iota, or if you want, cos iota. And now, if I look back at my polarizations, I know iota, I know the chirp mass, what is left is dl. And this is how basically we can constrain dl. Because otherwise there would be degeneracy between, for example, dl, iota, and m.
I've been wondering, are we able to measure this ratio of polarization amplitudes? And if not, why not?
Well, so basically, here I'm assuming that we can measure the amplitudes and that we can measure both. Here to constrain iota, because iota basically from this equation you need to have both.
But I guess that's my question. Can we do that? I
yes,
think not,
we can do that, but
why not?
Not always, because, for example, you can see that H cross here directly depends on cos iota, and when cos iota is 0, h cross is equal to 0. So in that case, for example, we cannot really kind of get direct information on cos iota, only looking at h plus.
So I mean, really at the data level. So right now, let's say we have three.
Absolutely, yeah.
But so.
Yeah.
How many detectors do you need?
Well, I guess, at least 2. But I think, I mean, with 1 in general, it's not possible. Of course, the more detectors you have, the better it is also for other reasons, because this helps also in the sky location, in the sky localization. But in general, yes, I would say that this is like the argument behind the assumption that we are able to constrain both, but if it's not, I mean, it's not always the case that we can really kind of constrain both always. But today we can. I mean, it depends also on the geometry of the system and on other parameters of the waveform.
I'm really struggling to find a reference that tells me, for example, for, let's say, one event where the 3 detectors were run, what's the strain of H plus and H cross? I don't know if that exists.
I mean, the strain amplitudes. So first of all, what we measure is a combination of the 2 polarizations, right? And that combination is a linear combination, and it is multiplied by the antenna pattern functions of the detectors, which in case of LVK are they depend on the angles, so I think that in general, like you are able to constrain both, but it depends on the system, on the geometry of the system, and also on how many detectors you have.
So just to make sure, I think LISA can detect both polarizations by its own, right? With LISA, you do not need 2 detectors.
But this is 3 detectors that are all together, so
yeah,
it's a triangle.
Okay.
Yeah, I mean, if you consider LISA like as a single detector, okay, yes. But in the end, you will have like at least two data strains. So, okay. This was just to show basically why we, in general, can obtain information on DL. So there is a problem, right? The problem is that in DL, to obtain DL, there will always be some degeneracy between this parameter and, for example, iota. And so we have to be able to break this degeneracy in some way. This is one example, but there are also other ways. For example, if we observe an electromagnetic counterparts and we get some information from the observation of the jet, for example, of the electromagnetic counterpart, then we can get a better constraint on iota, and this implies also a better constraint on DL. Okay, so in the end, as I was just saying, what we measure is a combination of these polarizations. And in the end, I mean, this was just, a theoretical way, if you want, to get an idea. But what we do in practice is Bayesian inference, okay? So we do parameter estimation. I have a waveform, which is, for example, function of 9, 11, 13 parameters, which include DL, which include iota, which include M1, M2, the spin of the 2 objects, A1, A2, expressed in a Cartesian component. So this gives me other 6, if the waveform is able to include that. The array deck, so the position in the sky, the phase at coalescence, and the time of coalescence. So all of these parameters, we need to sample them together. And in the end, we also get an estimate of the luminosity distance, which in most of the cases is not super good, especially when we have only 2 detectors. When we have 3, of course, because of triangulation, it's a way better. When I say it's not good, I mean uncertainties can go up to 30% or something like that. So it's a big uncertainty if you consider that the measurements, distances can go up to gigaparsecs. But in any case, so the concept here is that these sources give us the luminosity distance without the need of any distance scale ladder. This is typically what is done with electromagnetic sources, right? You start from the object that you're able to measure nearby, close by, and then you move step by step, with several techniques, parallax, Cepheids, and so on and so forth, up to the very distant ones, which include also well, of course, the supernovae 1A, which have been used to do cosmology, for example. And you do this like, anchoring yourself step by step, and also calibrating every step, each step of the ladder, if you want, with the previous measurements. And so this is typically like one of the things that people have to be careful when measuring distances with this technique, because in general, there can be calibration systematics, okay? But in this case, GWs don't suffer from this, because we are not using any kind of calibration for the luminosity distance. It's basically GR, which calibrates the signal for us, okay? And now, coming back to the expressions that I showed you here for the polarization, how then can we use this information to make cosmology, late-time cosmology? Well, if you think about the expression for the luminosity distance, this is a function of redshift, which is actually including cosmological parameters. We have the Hubble parameter, which is the rate of expansion of the universe measured today. Plus, we have other things, right? We have the matter density of the universe. This is the ratio of rho matter over the critical density. Think of it as a parameter which can go from 0 to 1. The same goes for omega lambda. And in general, say that I don't have this term, there is a constant that you can derive from Friedmann equations that tells you basically that the sum of these two terms must be equal to 1 in a flat universe. But the point is that it is very interesting to actually use these systems to constrain H0, the Hubble constant, omega matter. And so this is the way that we want to use actually standard sirens. And the idea is similar, if you want, to what is done with supernovae 1A. There, I mean, the observables are different, but basically what we want to do is some kind of Hubble plot. Maybe I should place myself here. Some kind of Hubble plots where you have the redshift, the distance modulus as a function of redshift. The distance modulus is just an expression for the logarithm of the luminosity distance. And it's basically given by the absolute magnitude minus the apparent magnitude minus the absolute magnitude of the object that you observe. And so these are called standard candles because we are talking about electromagnetic signals. And with GWs, we talk about standard sirens. And the reason, just because of the analogy, if you want to, to sound waves, maybe, it's more appropriate because we're not really seeing the gravitational waves. But in order to do this, there is one thing which is missing, which I haven't talked about yet, which is the redshift. I mean, I've talked about it, but not in the way that I need, in order to use this the luminosity distance redshift relation. And so, yeah, this is something that we cannot really obtain from the waveform itself because the redshift is degenerate with the mass. So if I look at a single event from the parameter estimation itself of that signal, I cannot really extract the redshift. This is something that when you look at a paper, for example, I don't know, like a catalog paper of GW events, sometimes you will see properties of the sources, for example, the masses, expressed in source frame. Those are actually quantities which are derived from the detector frame mass divided by the necessary factor of 1 plus z, assuming a cosmology. Okay, so the redshift is something that we cannot get. And so then the question is, how do we get the GW source redshift? This is actually a question I want to ask you.
If you can localize very well your source, maybe you can look at which galaxy it belongs to and find the redshift by the electromagnetic spectrum of the galaxy.
Okay, yeah. That could be one possibility. So the electromagnetic counterpart. Okay. Then?
Basically do statistics if you know like roughly enough what the population of binary micro systems is and observe many of those signals, you can try to infer that.
Okay.
So there are perhaps some processes that tend to happen at particular mass scales, or like particular size binaries. So then we could, from that we could see the masses of the binary, and therefore then we could do the frequency at the time of emission, or something like that.
Okay.
Or use the fact that maybe for neutron stars you roughly know their mass, and so you can estimate their redshifted mass. I don't know.
Maybe. Okay. So first method, electromagnetic counterpart, right? So the point that has been done and has been made. We are able to identify a direct electromagnetic counterpart to the GW event. We have a confident association with that. This is usually called the bright siren method. Why bright? Because we have light, no? Electromagnetic. What is the problem with this method? It requires an electromagnetic counterpart, no? And so far, we only have one event with a confirmed electromagnetic counterpart. So we need to think about some other ways. We want to still kind of exploit these observations, because we had something like around 300 detections. Not 300, but 216, I think, from the last. I will talk about this, but the latest data release from the Lago Virgo Cagra has more or less 210, 220 compact binaries. Statistical methods. So, for example, one could use spectral features in the gravitational wave mass distribution of the compact objects that we observe. I will show you in detail what this means, because it's a bit, it's not trivial in my opinion. But basically what this requires is to make some assumptions about the gravitational wave population. So I can still use my gravitational wave events, which don't have any electromagnetic counterpart, to make cosmology, because I'm using the fact that I know some properties of these, for example, black holes, because we mostly have black holes. For example, the distribution of the mass of the black holes. I will show you why we can use this distribution to actually obtain the redshift information. But this requires some assumptions. So this is something that we have to put in our analysis, and we have to, we always have to remember that we are making some assumptions and choices. And then there will be statistical methods maybe that allow us to judge which model is better. For example, if you remember maybe from Stas' lecture, Bayes factors could be one way. And then the third method that I will go into in this lecture is by using a galaxy catalog. It means that on top of this information, which in any case we have to use, and meaning that we also have to make some assumptions about the GW population even with this third method, we can add redshift information if we have a galaxy catalog. Why? Because basically if I have a very well localized GW source, and I have a galaxy survey, for example, that covers that patch of the sky, we can make the assumption that the GW source is hosted by a galaxy. I can then cross-match this information, if you want, the sky location which I get from the GW source itself with the galaxy catalog. This will boil down to only a sample of galaxies which might be the potential host of the GW source, and then I can use again statistical techniques in the framework of hierarchical Bayesian inference to basically extract the redshift information and to see which is the most probable host among all of those galaxies which might be compatible as being the host of the GW source. What is the problem with this? Well, we need a galaxy catalog, and so far the galaxy catalogs we have been using, as I will show you, they are not very complete, or if you want, deep. This means that we are missing a lot of the actual galaxies which are there. And so in this case, our framework is such that the information that we are getting from the measurement of the GW and the galaxies is actually kind of coming mostly from this other method. And we need also to correct for selection biases, which affect the galaxy catalog, because in general surveys have, you observe with some telescope which will have some kind of limited flux. And so this will also limit, in practice, the sample of galaxy that you will be using. And you have to correct for that, because otherwise you will get a bias. And yeah, so on Friday, I will go more into the details of these three methods, and I will recollect also what we know so far from the LBK. And finally, in the end, I will also tell you a bit more about massive black hole binaries, because they can be used as bright sirens, as Alberto will tell you tomorrow, I guess, or on Thursday, and MRIs, because MRIs can be used as dark sirens. Okay, I think I will probably stop here.
Thank you very much, Danny. Are there final questions? No, otherwise, yeah, thank you again, and we'll reconvene your next lecture. I know that some of you wanted to organize movie night, so I don't know if you want to make an announcement for that. If there is a selected movie or okay, I mean this can be later, right? Okay.
Cool.